Okay, we're about to get going. I'm going to share my screen so we can all take a look at the general agenda and some other stuff I'm going to show you. Okay, did I start recording? Yes. All right, chat. All right, this is what we're looking at today. We're going to formally define free fall as part of our vertical motion and kinematics and be able to identify when that's present when we're looking at a problem. We'll do some couple example problems today together. There made some changes, you'll see up here, I made some changes to the assessment question guidelines that I think make them a little better, a little more open-ended. We'll look at that first. Then we'll talk about free fall and acceleration due to gravity, work some example problems. The agenda for you to do is pretty much the same stuff, reminding you of what's in the content library new for this week. The lab report for this week has been assigned. It's due next Wednesday. And so this stuff down here is about the lab report. I'll show you where you can find the details about it. The lab report is posted as an assignment, just like an assessment question is posted as an assignment in the assignments tab. So if you go to the assignments tab and find the lab for this week, which is the Nerf Dart Launch Velocity Lab, Lab 2.1, there's an attachment on the assignment that gives you details about it. But they're also the same details that are in the class notebook under the labs section. So it shows you the same stuff, but this in two places. You want to make sure that you look at the video I did, this one, how to do a lab report. I did an example lab, and then I showed what a lab report would look like. Your paper is basically set up the same way as an assessment question. You have 4 parts to it in rows or quadrants. You got a diagram, a labeled diagram of your lab setup, a listed procedure in steps that shows how you're measuring stuff, what you're measuring it with, what the units are that we're measuring stuff. And you take those measurements in the video. When you see the video, you'll see I slow down the slow motion camera, kind of freeze it so that you can take a measurement with whatever measurement device is there. Then you got any analysis. Either you're doing just a data table or you're doing a data table and a graph. This Nerf Dart Launch Velocity Lab, you don't have to make a graph. You can just record the data, handwrite a table, or you could do a little Excel or Google Sheets table. Again, just look at the how to do a lab report video. And then you got a conclusion at the end of it. Those are the 4 parts: diagram, procedure, analysis, and conclusion. So we'll make sure we look at that. Practice problems are in there. That's the same thing. Okay, so we got slightly different assessment question guidelines, which I think are a little easier. So we'll look at those. We'll go look at that first, then where the lab stuff is. Then we'll talk about free fall and do some example problems. Okay, and make sure you've set in a assessment question, reassessment request. If you want one, you need to submit that today. All right, first things first. Let's look at these, how I changed the assessment question guidelines. It's still the same format, right? It's still the same thing. I've just made it a little more open-ended. So I've said for baseline state laws, theorems, principles, equations, type of visuals that you're going to do. So basically that whole section should just be, the baseline is what kind of stuff are you going to use to solve the problem. So kind of basically the same as what we had before. So you might say, if we're talking this, this question this Friday is going to have accelerated motion, most likely. You might get one that just has constant velocity motion. I don't know. But you could say one of those principles. Then you could say, I'm going to use the kinematic equations. You could list them if you want, because that's going to be helpful for solving the problem. And then for visuals, you could say motion graphs, or maybe you're going to draw some other sketches to help you solve the problem. That's fine. That's baseline. The visual, I've reduced it to just say provide visuals that represent the motion of any objects relevant that'll help you solve the problem. So that might be motion graphs, but I'm not saying you have to draw all 3. You draw whatever is going to help you solve the problem. You still need to draw them correctly. If you say, I'm going to use motion graphs, and then you draw wrong motion graphs, you're not going to get points for visual, obviously. But I made it a little more open-ended. You draw whatever motion graphs you think will be helpful for you to solve the problem. And other sketches that you might want to do too. Quantitative, this is where, I mean, we're using our kinematic equations now. That's the quantitative stuff that we should have in there. And then qualitative, I've changed, instead of saying, if this changes, like if the acceleration doubles, what's going to happen to the displacement? No, I've made it much different. I've just said use complete sentences to describe how you applied this other stuff, the baseline, the visuals, the quantitative work, describe how you use that to solve the problem. Okay, so it still should be in complete sentences. It should definitely be more than one sentence. It should always be 3 to 5 sentences. You could describe the motion of each of the objects that are in the scenario qualitatively that supports your reasoning from the other components, like the math component or the visual component. This could also be a thing where you could kind of think about qualitative is like you solve the problem and now you're kind of teaching somebody else how to do it. So that could be like explaining your work, basically. Okay, so it's a little more open-ended. It's you showing with words and complete sentences, qualitatively describing what you did to solve the problem. And all of those pieces should be consistent. You know, your baseline, your theorems, the equations you intend to use, the visuals, that should be reflected in, you know, the visual component, the quantitative component, and qualitative should all kind of mesh together. Okay, so that's all. It hasn't changed that much, but I've tried to make it a little more open-ended since people tend to take different routes to solve problems, which is good. You should encourage that. So there's the slightly different assessment question guidelines. In the labs section, so now I'm up here, I've just opened the little section, how to do a virtual lab report. There's the link to the example lab video. Make sure you watch it. In that one, I've made a data table and a graph for the analysis section. This current lab this week, the Nerf Dart lab, you don't need to have a graph. You could do this entirely on paper, or you could have a few of the components written on paper, and then you submit a second picture that's got your data table if you want to keep your data table in an Excel or Google Sheets spreadsheet. But all that's in this example lab report. Watch it. So here's all the information about this week's lab assigned this morning. It's due Wednesday at midnight. This is the same thing that appears in the attachment on the actual assignment. So you have an objective, determine the launch velocity of the Nerf dart, how fast it's leaving the barrel of the gun. It's being launched vertically. The rubrics here, so 0, 60, 70, 80, 90, 100. Notice in this one for the analysis, I tell you, you don't have to have a graph, but you do need to have data recorded, measurements recorded, and neatly organized, labeled, all that stuff. And then there's also a link here to the lab video that you can click and open in YouTube. The lab videos, you're going to want to be able to probably watch them larger, full screen, so probably open them in YouTube on the YouTube website. And you want to be able to pause, go back, especially in the parts where you take a measurement, where it slows down, you want to be able to pause it and see where the object is, what the measurement is. You read the measurement straight from the video. Any questions so far about what we're doing, how you can access the lab information? I think the assignment should be already posted, so you could find it in the assignments tab right now. Any questions about how you might find the lab information, how we're going to submit it? Same as just like an assessment question. You do your work on paper, take a picture, attach it to the assignment and hit submit. Or if you're using what quantity are we using? You'd have to watch the lab video to know what quantities are being measured. Kennedy, I'm not answering your question. So like if you see me put something on, excuse me, you see me put something on a triple beam balance, I'm measuring mass, right? You see me have some meter sticks lined up and we're measuring a height or a distance, you'd be like, oh, we're measuring length, that's the quantity. Or height, whatever, or width, or distance, whatever you call it. Okay, so we've gone over the where to find the lab stuff, our slightly different assessment question guidelines. think that's all we wanted to do. Okay, so we're going to do some notes real quick on free fall and acceleration due to gravity, and then hit the example problems. So I'm in content library. Let's go up to notes. And we'll wait a minute for it to load for everybody. The last thing we had was all this stuff on our kinematic equations. All right, we had two columns. Left column was just the subscripts for x, meaning motion in the horizontal direction. And then the same for kinematic equations on the right if we're talking about motion vertically. We're talking about free fall and the acceleration due to gravity. That's vertical stuff. So if we have a problem that just involves something moving vertically under the influence of gravity, for instance, then we're going to have y subscripts. And if we talk about its change in position vertically, we're talking about a delta y. But it's still the same equations. So make a new section down here. We're just going to put in some notes about free fall and acceleration due to gravity. We should have a working definition of just what free fall is. So by free fall, we just mean it really is defined as just the motion of any object under the influence of gravity alone. So you say you forget no other forces are acting on this thing, just gravity. That's all free fall is defined as. Motion of object under the influence of gravity alone. No other forces. So there are a couple YouTube videos. There's one of this professor at a NASA facility. They pump all the air out of this giant vacuum chamber, and they drop a bowling ball and some feathers. First, they drop it with the chamber full of air, like normal atmospheric pressure, and the bowling ball hits the ground first, and the feathers are experiencing air resistance and slowly falling. They pump all the air out, so there's no more air resistance, and now they're in free fall conditions. The only force acting on the feathers and the only force acting on the bowling ball is gravity. And they fall at the same rate and they hit the ground at the same time, even though they have very different masses. So it's important to see that difference. Once you get rid of this air resistance and you have the only gravity acting on these objects, then they experience the same speeding up. And if they experience the same speeding up, then they end up hitting the ground at the same time, even though one's very massive and one's very low mass, the bowling ball and the feathers. So one key takeaway is that in free fall, all objects, regardless of their mass, experience the same acceleration. That means they speed up at the same rate or they slow down at the same rate. If I drop something or throw it downward, then they're going to be speeding up because gravity always pulls things towards the center of the Earth. And when we're just, sitting here, we call that down. So if I throw something downward or I drop it, then objects are going to experience the same rate of speeding up, the same downward acceleration. If I throw something upwards, it's going to slow down, right? Because gravity is pointing downwards. And so that acceleration is downward. I throw it upwards, the object slows down until it comes to a stop at its highest point, and then it's going to start speeding up in the downward direction. If I throw two things with different masses, right, like my coffee cup and this apple, I throw them up at the same speed, they're going to slow down at the same rate, stop, and then start speeding up at the same rate as they fall down. If it's something like a feather and there's air resistance, it's going to be different. But we're not saying there's any air resistance. We're forgetting about all air resistance and keeping it simple and using free fall conditions. The only force acting on stuff right now is the force of gravity. So in free fall, all objects, regardless of their mass, experience the same acceleration. This acceleration near the surface of the Earth is called acceleration due to gravity near the surface of the Earth. And it's a certain value, a constant value. It's about 9.80 meters per second squared, and that equals little g. That's what we call the acceleration due to gravity near the surface of the Earth, we give it the lowercase g. So if you ever see lowercase g, that's the value it's talking about. Okay, this would be our acceleration in the y direction, or AY, one of our kinematic variables in the y or vertical direction. So we got an object moving vertically. Either it's moving upwards or moving downwards, or it does both throughout the course of some scenario. And we have free fall conditions, we know the acceleration. If it's doing that vertical motion at all, we know its acceleration, AY, in the vertical direction is going to be little g. Okay, here's an important thing. In labs that we do, because gravity will frequently affect what's going on in the labs in the room, like all the time. So in labs, we use little g equals 9.80 because that's the actual value of it. In problems or assessment questions, not labs, but in problems and assessments, you can use little g equals 10. Because it's slightly less of a headache to just use 10, and we care about the process of solving these problems, we don't care so much about the exact numerical answers that we get. In the lab, we do care about the numerical answers that we get, so we got to use little g equals 9.8. So when you're looking at this lab where I shoot a Nerf gun dart vertically, that's in the lab, that's in reality. There's going to be a vertical y direction acceleration, slowing it down because that acceleration is going to point downwards. And in that lab, because it's a lab, you should use little g is equal to 9.8 because that'll get you a more realistic answer because the lab is happening in the real world. When we're solving our practice problems or assessment questions, we just use g equals 10. And I always write on the assessment questions, ignore air resistance because we're not dealing with that. And you may use a little g equals 10 meters per second squared. Okay, so we got a basic definition of free fall. The acceleration due to gravity is this little g. This we might also point out that the acceleration due to gravity near the surface of the Earth is always little g. It's a constant. But if we go to another planet, go to another moon, somewhere else in the universe, little g is not going to be equal to 9.8 meters per second squared. It's going to be different depending on the mass of that moon we go to and how far away we are from the surface or the center of that object. So little g being equal to 9.8 meters per second squared, that's just at the surface of the Earth. And that's what we're talking about. Everything we're dealing with right now is near the surface of the Earth. But just know if we go somewhere else, it's going to be different. And you can actually see that in the Apollo videos from astronauts on the moon. There's a good video I forgot to link to from, I think, Apollo 15, where one of the astronauts was dropping a feather and a hammer at the same time. And they hit the ground of the moon at the same time, but they didn't fall as quickly. They didn't speed up as quickly as they do on the Earth, because on the moon, the acceleration due to gravity is 1/6. Acceleration due to gravity on the moon is 1/6 of what it is on the Earth. Okay, those are the basics. Those are the basic stuff. We already have the kinematic equations. So one of the main takeaways here is that this acceleration due to gravity is a certain value. That's our acceleration in the y direction. We can use 10 meters per second squared equals g in problem solving for the acceleration in the y, but 9.8 in the labs. So let's take a look at a couple practice problems real quick. I think we had done 3 together. That was a little horizontal thing going on. That was the first one where we went thoroughly into what we needed to do in order to use our kinematic equations properly. So I'm going to find one where we have an object moving vertically. Okay. I think this is one where, excuse me, an object is just dropped. Okay, so a stone is dropped from rest from the top of a building. It takes 3 seconds to reach the ground. What is the height of the building? We might as well go through and just be clear about what our baseline would be for this. It takes 3 seconds to reach the ground. Something is being dropped vertically. Is it undergoing constant velocity motion or uniformly accelerated motion? I got to think if an acceleration is going to be present here or not. And we have gravity affecting it, making it speed up as it falls. That means its velocity is changing. So we have uniformly accelerated motion. What else am I going to use? I'll draw some motion graphs. I'll use some kinematic equations. I probably don't know exactly which ones I'm going to use until I get into the problem, so I can just write kinematic equations. I don't have to do visual first. Maybe I want to do the quantitative and just solve the numerical part of the problem with my equations first, but I'll do a visual. Let's make this a position versus time. Now I look at my picture I got here, or if I just had the description of something being dropped from the top of a building, I know it's going to start at a high position and it's going to be in the y direction. So I probably want to put y there instead of x. It's a vertical position as a function of time. It's going to be speeding up in the downward direction. So let's think if this is actually my building, like if I took this picture, like my building's right here. That's kind of what we're representing in the y-axis. This is our building. And the ball is starting from the top, right? It's going to be released from up here. So that's where my function is going to start, not at the bottom, but at the top, the high y position. It's going to be speeding up in the downward direction, so it's moving towards the ground. So this is going to be, what does speeding up look like? It doesn't look like that. That would be linear, right? That would be not speeding up. We know if we're speeding up or slowing down on a position versus time graph, then we should have a curvy line. And my slope should be getting steeper. That's what I have speeding up if I'm moving in the downward direction. This would be at 0 meters above the ground at the very end, where I just put that dot later in time. And so you can see if I draw in slopes here, there at the very beginning I would have a 0 slope. A little later I have a steeper slope. I'm just trying to slope at a point on this curve. And then I have an even steeper slope. So as a slope gets more steep like this, it's traveling in the positive direction. And the slope is our velocity. If it gets steeper, then it means it's speeding up. 0 slope on position time means we have 0 velocity. We're sitting still. And if my slope is negative like that, that just means now we have a velocity. The slope is steep. It's just negative. That means we're moving in the negative direction. So we already have which direction is positive and negative. By convention, we call down negative. So as the slope gets steeper in the negative direction, that means we're speeding up in the negative direction. And that's what happens when we drop something. If I did a velocity versus time graph, this would be velocity in the y as a function of time. Let me think now, what happens to our velocity? I'm going to release it from rest. Notice in our picture we have some extra information, right? Really the information from the description, but our velocity at the very beginning is called v0 up there. We could call that v initial. Doesn't matter what subscripts we use, but we're dropping it from rest. So that means the velocity starts at 0, right, if it's dropped from rest. So there's my first point on my velocity time graph. It's going to speed up in the downward or negative direction. So that means that its velocity is always going to be negative. Remember, the plus or minus tells me the direction. So that means I need to draw this into the third quadrant. Negative velocity. It's increasing its speed in the downward direction. Downward is negative, so I'll always have a negative velocity. It starts at 0, right? There's 0 velocity. And then here would be some whatever the final velocity is going to be down there. Here's the initial velocity right there where we start. Acceleration. Acceleration is going to be easy for every problem involving free fall because it's always the same. Notice I'm drawing my, oops, come on. I'm making my graph slightly larger so that I can do the first and the fourth quadrant. Please don't tell me my computer has frozen. Looks like it. But my acceleration, we know if we're dealing with free fall, the acceleration is the acceleration due to gravity. So that's going to be little g. So it's going to be a negative acceleration. It's pointing downwards. And we're going to be moving in the negative direction. So I'll have a negative 10 meters per second squared. Since I'm doing the problem and not the lab, I don't need to use negative 9.8. Oh, I'm completely frozen. Awesome. Okay. I don't know how it's still sharing my screen because I just shut that computer off. All right, bear with me for just a moment. All right, at least it reboots fast. Our technology is definitely ready for this level of stuff. Okay. What was he doing? He was talking about acceleration versus time graphs. That's what I was doing. This is AVT. It's acceleration in the y direction. Here's my t. The acceleration is acceleration due to gravity. Think about what direction it points. Downwards. Okay, so that's going to be our negative direction. So I can write, I'm going to have this flat line right here. Acceleration is always going to be zero slope in our class. It's either going to be 0 or some non-zero y equals something, some number. So this is little g down here. Okay, so these actually look exactly like our car speeding up, except things are reflected over the x-axis. right? It's still the same shape. I got a curvy position time, I got a linear velocity time, I got a flat acceleration time. Alternatively, if you have a question that doesn't have a picture, like, drawing that picture at the top that I just provided, that's another type of thing to add to the visual that's going to support and help your work. Drawing something is really helpful for every physics problem we do. But our motion graphs are the more, math-like, precise way to do our visual. All right, quantitative. We want to get this information. What is the height of the building given what we know? We're gonna have to use some kinematic equations. They're in the y direction. You don't have to list all of them. I'm just gonna put them here to remind us. I got v final in the y is equal to v initial, that's velocity, initial in the y, plus acceleration in the y direction times time. I got the one that starts with displacement. This is the quadratic one. I got my velocity squared one. This is the third kinematic equation that does not have time in it. And then I've got my very last one from our, delta y, 1/2. Okay, so there's what my toolkit has for equations, the quantitative section. We said it's good to list what we know, what we don't know. I go back, look at this question up here. A stone is dropped from rest from the top of a building. Dropped from rest always tells me the initial velocity in the y direction is 0. That's something I know. I indicated that as such in my velocity time graph too. It takes 3 seconds to reach the ground. Okay, so that's t equals 3 seconds. And it's something I always know with a free fall problem is the acceleration in the vertical or y direction is little g, which we're going to call 10 meters per second squared in a problem. But I got to be careful. What direction is that? I can look if I did my visual already. I know this is going to be a minus 10 meters per second squared because I called down the negative direction. You could also look if you need to define the final velocity in the vertical direction. That would be right down here. That would be a negative number. All the velocities after it's released are going to be negative because it's moving in the downward direction. That's dependent on knowing just what velocity means, how fast and what direction. How fast is given by the number with the units. What direction is given by a plus or minus sign in front of it. Same thing with acceleration. Okay, what's unknown? I'm asked to find the height, so I want to find delta y. And what other thing don't I know? Remember, there are 5 kinematic variables. I also don't know v final in the y direction. But what I want to find out, hopefully I can just use one equation here, is delta y. That's the height, the change in vertical position. So I go back and I'm looking at my kinematic equations here. I know vi, t, and acceleration. Initial velocity, t, and acceleration. Which one should I use? Well, I want to get delta y. I have initial velocity in the y. I have time. I have acceleration in the y. I have time. So that looks pretty good right there. Also remember, a helpful thing to do is if you ever know that something is 0, go ahead and substitute that immediately and simplify the equation. So we're going to go with this kinematic equation number 2. I'm going to copy it down in its original form before I start really messing with it or substituting anything. So my delta y is going to stay there because that's the change in vertical position. That's going to give me the height of the building. Initial velocity in the y is 0. So that means this entire term is 0. So we just rewrite the equation without that term in there to simplify it. I know the acceleration in the y direction is little g. So it's going to be 1/2 g times time squared. And this would be the exact same way if you were asked how far does a car travel if it starts from rest it accelerates at 10 meters per second squared for 3 seconds. It'd be the exact same setup, except you'd have, horizontal stuff, delta x, acceleration in the x, and time. So we're just talking about something vertically, and with free fall, we always know the acceleration is going to be little g. You got to be careful with the pluses and minuses with direction, though. We've already isolated, or we already have delta y, the vertical change in position, which is going to be the height of our building, isolated, so we don't have to move anything around. We can substitute. So I have 1/2 times, I'm going to use -10 because it's a problem, not a lab, instead of using 9.8 or minus 9.8. And the time is 3 seconds. So you solve all of that at once, or whatever you want to do. 1/2 of times -10 is going to be -5 meters per second squared. I'm going to multiply by 9 seconds squared. All right, because I do 3 squared and you do seconds squared. Notice what happens to my units when I multiply these. The second squared goes away and I'm left with meters. That's good because it's a displacement. And I have -5 meters times 9 is -45 meters. That's the vertical change in position. So we had a building, right? We had a ball that starts at the top of the building, and then it moved in the downward direction. This is where it started from. So there's 0. This is the y direction. Here's -45 meters. So that's what our -45 meters means, is that the ball, starting from 0 position at the top of the building, had a change in position in the negative direction, downward, of an amount 45 meters. That's why it's negative. If I'm answering the question, I'm probably not going to say delta y equals that. I'd say height of the building is 45 meters. You don't give a height of an object in negative meters, right? So this would be my final answer down there. I'd address the actual question. The height of the building is 45 meters. So same sort of setup, same sort of process. The baseline, not the baseline, the qualitative part, since we slightly updated that, that's like explaining how we solved the problem in 3 to 5 sentences. All right, what did I do? So let me see. I could say, this is a free fall problem. That's something I know. There's a free fall problem. I used motion graphs. I used kinematic equations where the acceleration was little g in order to solve for the delta y vertical change in position, because the vertical change in position is going to tell me the height of this building. Basically what I would write. It's a free fall problem, therefore ay equals little g. What did I do first? I used motion graphs first. I did a visual. I used motion graphs to set up the problem, because that gave me an idea of, I'm going to have a moving in the negative direction. I got a constantly increasing velocity in the negative direction, and my acceleration is going to be this negative 10 meters per second little g. So I used the motion graphs to kind of help me set up the problem. I used kinematic equations. I used only one. I used a kinematic equation with delta y so that I could find the height. That's what the question was about. Could find the height of the building. And I knew initial velocity was 0 because it was dropped from rest. dropped from rest. And I knew acceleration in the y was little g, since it's a free fall problem, or free fall conditions apply. And time to fall was given as 3 seconds. You know, something like that gives a description of what you did in a few sentences, 3 to 5 sentences. What did you use? You can kind of think about if you had solved a problem and one of your classmates was like, I don't understand how to do that. What did you do here? 3 to 5 sentences to kind of quickly explain that as if you were teaching or explaining it to somebody. That's what we're looking for in the qualitative. This is one of our simpler little free fall problems. But we're doing the same sort of stuff. It's about 8 o'clock. I'm going to point out some practice problems that are worth solving because my assessment questions tend to they're a little more complex and I think a little more interesting and worth solving than something really simple like this problem we just did is straight out of a college physics textbook, like the very first free fall problem they show you. You just drop an object. This one is relevant for the lab because it's still kind of a simpler problem, but instead of dropping something, we're throwing it upwards. So we know, for instance, that our initial velocity here, we flip a coin, we throw it upwards. The initial velocity we call up positive is 5 meters per second. When it gets to its highest height, just like this Nerf dart that I launch vertically, when it gets to its highest height, we know it stops for an instant. That's very important. When it gets to its highest height, whether it's this coin being flipped or it is our Nerf dart being shot upwards, at the highest height, its velocity is 0 for an instant. So we can call the maximum height our final position, where we would describe our final velocity being 0. So I could say v final equals 0. We always know this is another free fall problem, so make sure if it's just like in the lab's going to be a free fall problem, basically. We know acceleration in the y is little g. We're calling down negative, so this should be minus 10 meters per second squared. In the lab, you're not going to use minus 10. For a lab problem, you're going to use minus 9.8 because that's the actual value. In this particular problem, we're asked how high does the coin go above its point of release. So my unknown things are delta y. All right, delta y is going to be this positive change in position in the picture. So that's what I'm looking for. All right, that's what I would say. That's the thing I'm trying to find out. But it's always good to list the other thing we don't know. We don't know time here, do we? So in our Nerf dart lab, this is the thing you're going to be measuring. Because I have the camera pointing at how high the Nerf dart's going. So you're going to know the delta y by taking a measurement. And what you're asked to find out in this lab is how fast does the Nerf dart leave the gun? What is that going to be? You're going to be looking for the initial velocity. So it'll be flipped in the lab. In the lab, you're going to know delta y by taking that measurement from the meter sticks. And you're going to need to find the initial velocity. That's going to be how fast the Nerf gun leaves the barrel. And we also know the final velocity in the y direction at the highest height is 0, because we're saying initial velocity is at the beginning when it's launched. Final would be at its highest height. And we always know with free fall involved, the acceleration is going to be little g. So this problem is very, very similar to what the lab question is about. Some of the other ones we have in here that are good to look at. These are more like what my actual assessment questions look like. A larger description of a problem, like this Batman problem or the Tony Stark one. There could be different types of motion involved. So like as an example, let's look at this one. Basically what's going on, Iron Man's near the ground and he needs to get up to the top of a building. So we get some information like he has enough power in his suit to accelerate upwards at a constant rate of 50 meters per second for 3 seconds, after which his suit will be out of power, rockets shut off, and free fall conditions apply. So he's like accelerating upward and speeding up, just like a car that's traveling horizontally is speeding up, but then you take your foot off the gas. What happens? The car continues to move at whatever maximum speed it reached. Right, if we're accelerating upwards, like he's got a rocket at the bottom of the Iron Man suit, he's speeding up vertically, and after 3 seconds, the rockets turn off. So free fall conditions apply. It's just like you throw something upwards, it's going to keep moving up but slow down. And we have a certain height he needs to reach in order to get to the landing pad. Will he make it? So right, you're looking for delta y. And this one's really good to figure out what the motion graphs are going to look like. For 3 seconds, he's speeding up. So there's 0 seconds to 3 seconds. What does speeding up look like? Right, it's curvy, it's parabolic, it's quadratic. He's speeding up faster and faster. This is the 3 second mark. And then at the 3 second mark, he continues to move upwards. So he continues to move in the positive direction, but now free fall conditions apply, meaning his acceleration has changed to little g, and he's slowing down. So then what's slowing down look like? And as soon as we get to a 0 slope, he's stopped. So at a certain later point in time final or something, he's going to be accelerating upwards, speeding up, then slowing down when the rocket's cut off, and then eventually get to some stopped position at his highest height. And hopefully that's the 1,300 meters in the question. We're going to try to figure out, does he make it? Let's see what just the velocity time. See, isn't this much more fun, a question like this? It's like, what is going on? Is he going to make it? I don't know. Okay, 0 to 3 seconds again. You can go back and you can look at one of the, I think it was motion graphs number 3 video that I made where I did multiple different motions in a single graph. There's some hints at how to break that up into portions. Okay, his velocity looks like increasing at a constant rate. Right, the rockets are on, he's speeding up with a constant acceleration of 25 meters per second squared or whatever it was. He's going to get to some maximum speed, and then the rocket's cut off, and now it's gravity that's trying to slow him down, so then he starts slowing down at a constant rate. So it'll look something like this. We don't exactly know what the steepness is, but eventually he'll come down to rest at T final at his maximum height. We're going to solve the maybe easier practice problems before you look at some of these later ones, but these later ones are the real ones. That's where they get fun. What would the acceleration look like here? We had given in the problem, he accelerates upwards at 50 meters per second squared for 3 seconds. So I got my 50 meters per second squared for the first 3 seconds. Sometimes it can be good to start with the acceleration graph. I mean, up to you. But then his engine's cut off, and it says free fall conditions apply. So after 3 seconds, we've got little g down here, minus 10 meters per second squared. And that's constant for the remainder of the time, slowing him down. There's an actual problem that doesn't come out of a textbook. There's one that makes you think more. So a lot of the actual assessment questions are going to be more like a scenario, not a simple, an aircraft speeds up along the runway, what's its final speed after 5 seconds? Now we want to see kind of weird scenarios we can analyze. So those are good to look at. We'll do some more practice problems tomorrow. And I'm going to make a couple videos today or tomorrow about some of the more advanced problem solving. So I'll solve some of these more advanced ones so you can watch that and just see those as examples rather than trying to take, half a class period to do it. But that's what we'll do tomorrow. You can look at, look at practice problems. You can look at those, might be the first thing to keep working on, and then look for video updates. And then you also have the lab you can work on, which is essentially a free fall vertical free fall problem. And that lab will be due on Wednesday at midnight. All the assessment questions are scheduled, so they'll post like usual tomorrow at 2:30 p.m., but we have class tomorrow morning anyway, so I'll see you again before then. Before we go, it's almost 8:10. We got 2 minutes, so post anything in the chat if you have questions before we go. Let me know. Thanks. You have a good day too. See you tomorrow.
Bye, Mr. Stacy.
Bye.
Mr. Stacy,
Yes, Kiara.
um, for that quiz yesterday, I do remember doing it during class because I remember when I logged in and it was like one question that I didn't understand, and then I went and I finished the test, and then I looked at the comments and somebody said that the number on number 4, I think they said, was messing up, like it would say that the answer was wrong.
Yeah.
And so I went back and I redid it actually. That's why I don't know how it didn't come up because I actually did it twice instead of once.
Okay, hold on. Let me pull up the. Just hold on one sec. Where's the forms? Here, since we got class together, I'm gonna write it down. I'm just gonna make a note to myself to go back and look at yours again. Maybe I can find it on the forums website instead of in Teams, but we'll figure it out. If I can't find it, I'll just like give you a private link to do it again real quick.
Okay.
Because the grade is just not showing up in Teams for some reason. I don't know why, but I'll make a note and then I'll send you an email or something to remind you today. Okay.
Okay. Thank you.
You're welcome. All right. Nope. I don't know why. Oh, these don't have the kids' names on them either. Yeah. All right, we'll figure it out.